Hello, so in this video we're going to look at the case where the Euler equation, okay, so we've reduced the Euler equation by choosing a suitable, guessing a solution is going to look something like this, y equals x to the power of r, then basically we've pulled out this equation again, okay, and we're going to end up, this is a basic quadratic, we solve it, and if we end up that the two roots are equal, okay, so this is the case we're going to look at here, where when we put, when we solve this equation, where we end up with r1 is equal to r2, we end up with a double root, okay, then we're going to look at what happens in this case. Now remember, we're always looking with the second order differential equation, we're always looking for two solutions, y1 and y2, regardless, okay. So basically what we're looking at here is for when r1 is equal to r2, so if it makes sense, if we just use this general solution over here, so y equals x to the power of r, then it just kind of makes sense, or not general solution, but you know what I mean. So y1 should be x to the power of r1, okay, and y2 should be x to the power of r2. But I've said here that r1 is equal to r2. I'm considering the case when r1 is the same as r2. So in other words, I can say here that y2 is also equal to x to the power of r1. So in other words, what I can say is that they're both the same, so I only end up with one solution. That's not right. I have to have two solutions for a second order differential equation. It just makes sense. If it doesn't happen like that, then I can confuse it with the case that I'm solving a first order differential equation, which I'm not. I'm clearly solving a second order differential equation because I've got the second derivative involved. Okay, so therefore I need to kind of distinguish these two roots in some way. So I'm not going to make them equal to each other. Okay, and the way which I do that, well, let's consider the case, if you remember from the case that, when we had just an ordinary second order differential equation with constant coefficients. So in other words, we had something that looked like this. Then we were guessing a solution that looks something that looked like this. Guessing a solution of the form y equals e to the power of rx, okay? And then basically what we said is, well, okay, we'll end up with two solutions. We end up with two roots, so r1 and r2, okay, end up with r1 and r2, and if they're both equal to each other, then we can basically say, well, y1 is going to be e to the r1 times x, and y2 is going to be e to the r2 times x, okay? But to distinguish the two, then we just stick an x here, and that's kind of the same thing here. But we're going to use a very similar idea here. Okay, but here, if we just stick an x in there, well, can you see then that what we're going to basically end up with is going to end up with x times x to the power of r1. So we'll end up with, if I just write this here, I'll end up with x to the power of 1 times x to the power of r1. So therefore I can just add the power. So I'll end up with these two things. That's not terribly useful. So in other words, I can't stick an x here. I have to be a little bit more creative. And as it actually turns out, I have to end up sticking a natural logarithm of x here. But I'm going to try and show you an argument of why we should stick a natural logarithm of x here. So in actual fact, there should be a natural logarithm of x here, not an x. But, hopefully you can see from these two cases, here we had an x, here we're going to have a natural logarithm of x. So here we have an x, okay, and here we have a natural logarithm of x because an x won't work. Okay, but I'm going to try and show you an argument of why that should be the case. Now, there's a couple of ways, or there's several ways that we can actually go about dealing with this. We could use reduction of order, and actually a really good exercise would actually just go through this in the same way to verify that we will end up with those two solutions just by using reduction of order to try and find y2. So we basically know that y1. We know that y1 is going to be x to the power of r1, okay, and I want to basically verify that y2 is in fact going to be natural logarithm of x times x to the power of r2 or r1. It doesn't matter, they're the same, okay. So you could use reduction of order to try and show that, okay. But I'm going to actually use a new skill. I'm going to show it in a slightly different way. The reason why is because I always think it's good to widen your mathematical vocabulary, to get you used to new techniques, okay, and to familiarise yourself with new techniques. Okay, but it will also help in the future because we will come across this method again in the future. So yeah, let's just go through it. So here's the idea. Okay, basically we're gonna use this. We're gonna use this over here. So we're going to end up with f of r. Okay, and we're going to basically say, well, okay, we're going to factorise this into the two roots because you can clearly see we're going to end up with equal roots. So we'll end up, we can factorise it in r minus r1 times r minus r2. Yeah, you've seen that before in a couple of videos ago. Okay, but of course r1 is equal to r2. So if we just replace this with r1, okay, what we'll end up with is r minus r1 times r minus r1. Are you happy that's just the same thing being multiplied together? So therefore that's the same thing as just squaring that. Okay, so this is basically what we end up with, and this is a double root. Okay, Well, okay. Well, look what happens if I put in R1. Okay, so let's see what happens if I put in R1 into this. So in other words, I end up, maybe if I do it over here, actually. If I put R1 into this, then I'll end up with R1 minus R1 all squared, okay, which is obviously going to be 0 all squared, so it's just going to be 0. Okay, then let's see what happens if I differentiate this. So let's see what happens if I differentiate this. I'm just going to do it by the chain rule. Okay, so the chain rule is the outie-innie rule. I effectively differentiate the outside. Okay, I differentiate whatever's on the outside, okay, and leave whatever's on the inside alone. So I effectively just ignore what's on the inside. Okay, I'll just keep that alone. So R minus R1. Okay, and I just differentiate whatever's on the outside. So differentiate whatever's on the outside, pretend that the inside's not there. So effectively it's going to be bring the 2 down, okay. Maybe if I just use that colour, bring the 2 down and reduce the 2 by 1, so that's just going to become 1, okay. Now what I'm going to do is I'm going to multiply it by the inside, okay. I'm going to multiply it by whatever's on the inside, so the derivative of that is going to be, I'm differentiating with respect to r, so I'm going to differentiate, r1 is just a constant, r1 is just a constant, so I'm just differentiating with respect to r, so the derivative of r with respect to r is just going to be 1, so it's going to be multiplied by 1, okay, so this is what I'm going to end up with. I'm going to end up with 2 lots of r minus 1 to the power of 1. Alright, and now let's see what happens if I put in R1 into that. So the derivative of f evaluated at R1. Okay, so what I'm going to end up with is 2 lots of R1 minus R1. Okay, to the power of 1, obviously. And that's obviously going to be 0. It's going to be 2 times 0, which is obviously going to be 0. Okay, so in other words, basically what I'm saying here is that I've got my f. Okay, this is my f, and I've factorised it into a double root. Alright, and when I evaluate R1, so in other words, my root, when I evaluate my root in there, I get 0, and that kind of makes sense, because obviously I want the right-hand side being 0. I'm saying what value, in order to get my R1 and R2, I'm saying what value of R will make this right-hand side 0, okay, and so fairly obviously R1 works, okay, but look here, the more crucial thing is that the derivative, okay, is also 0 at R1, okay, so I'm basically going to use that idea, and I'm basically going to say, well, okay, let's look at this thing here, now, okay. So if you remember a couple of videos ago, I said, well, this thing up here, my L of y, when I evaluate y equals x to the power of r in here, I end up with this step here. I'm just going to write it down for you. But if you're not sure where it comes from, go back a couple of videos and kind of see where it all comes from and everything. But effectively, when I evaluate y is equal to x to the power of r in here, I end up with this step here. Okay, so I end up with that. Right, I evaluate x to the power of r in here, and I end up with this step in here. And, like I say, if you don't see where that comes from, go back and see. Okay, but look, the reason, and if you remember that I defined that thing there, okay, by f of r. So in other words, I can just replace that by f of r. I can just replace that there by f of r. That's literally what I called f of r. Okay, well, I've just said that f of r is equal to that thing there. So in other words, I can say, well, it's going to be equal to, the x to the power of r is going to stay the same, multiplied by that thing there. So multiplied by, if I put it in red, r minus r1 all squared, right? So basically the idea is then, because f of r is kind of based on this, okay, I've just seen that the derivative of f, okay, and when I evaluate r1 is also equal to 0. So therefore, why don't I try differentiating that with respect to r? Why don't I differentiate that with respect to r and then set r equal to r1? So it's exactly the same thing as I've done here. So I've differentiated f, okay, and I've put in r equals r1 into that. So now what I'm saying is, why don't I do the same with L of x to the power of r? Okay, and let's just see what happens. So first things first, I need to differentiate with respect to r. So I'm looking now this thing here on the right. Okay, and I want to differentiate with respect to r. Okay. Okay, so the question is, what is the derivative of natural logarithm of r? What is the derivative with respect to r of x to the power of r? That's basically the question which I'm going to be asking now. Sorry, I think you saw the answer. I didn't realise I paused the video and hadn't unpaused it, so I'm going to go through it again. What is the derivative of x to the power of r? Well, basically, that's quite difficult. That's really quite difficult, and I have to basically use a special technique. Okay, when I say special technique, it's not actually that hard. Okay, let me just show you. Maybe consider how you would go about solving that problem, and I'll try and show you. Well, basically, the idea is the problem is that r is the power. R is the power. Now, the only thing I know how to differentiate where r is the power, where the thing which I want to differentiate with respect to is the power, is when this is to the base e. When this is to the base e. So I want it basically. The idea I want it to the base e. I want this thing written as the base e. Well, I can do that if you remember that x. So if you remember that e to the power of natural logarithm of x. Okay, what's that equal to? Well, if you set it equal to y, okay, then if I just rewrite that thing to make ln x the subject, so in other words, I just make ln x the subject, okay, well, in order to do that, I have to say, well, ln x is equal to the natural logarithm of y, okay, I've just rewritten that thing, just by power laws, you've seen that 100 times before, well, therefore, then I can just say that natural logarithm of x is equal to natural logarithm of y, so therefore, I can just say that y is equal to x. Okay, well look what y was equal to originally. Y was equal to this thing up here, so therefore I can just replace y with x. Okay, so in other words, I can just say that x is equal to e to the natural logarithm of x. I'm going to do the same thing here. I'm going to say, well, x is just going to be e to the natural logarithm of x. Okay, but that's still going to be raised to the power of r. That's still going to be raised to the power of r. That's still going to be raised to the power of r. So x in there is equal to e to the natural logarithm of x, but then I'm just raising it to the power of r. Okay, raising it to the power of r, like that. Okay, so it's just going to be that. Right. So now I can just say, well, okay, what is the derivative? Oops. What is the derivative of that thing there with respect to r? I can do that now. Okay, because if you remember that the derivative of the derivative, let's say, with respect to x of e to some function. So what's the derivative of that? Well, it's just going to be the function differentiated multiplied by the whole thing left alone. Yeah, you've seen that hundreds of times before, I hope. So basically that's how you differentiate e to the power of fx. It's exactly the same thing I've got here. Okay, it's exactly the same thing I've got here. If I just rewrite that, e to the natural logarithm of x. It's exactly the same thing I've got here, except my function now is natural logarithm times x. Well, natural logarithm of x is just going to be some constant because I'm differentiating with respect to r. So therefore, this is going to become ln x times r differentiated with respect to r. Ln x is the constant, so effectively it's just like saying, well, what's 2r differentiated with respect to r? Yeah, ln x is just a constant, just like 2 is a constant. So therefore, it's just going to be ln x, right? It's going to be ln x because differentiate 2r with respect to r, it's just going to become 2. It's just going to become 2. So therefore, it's going to be ln x times this whole thing left alone. So e to the natural logarithm of x times r. Okay, so now I can basically say, and maybe if I just convert that back as well, the e to the natural logarithm of x. Well, if x is equal to e to the natural logarithm of x, then e to the natural logarithm of x must be equal to x. So I'm just left with x to the power of r. Okay, so that was the whole thing, the whole point there. So it's just the product rule. Let's go back to the product rule. So I'm just basically trying to differentiate that thing there. So it's going to be natural logarithm of x times x to the power of r. That's basically what I've just shown there. All right. So there we go. I've differentiated that thing for you. But remember that f of r was equal to r minus r1 squared. I'm not quite sure I'm going to fit this in. So f of r is equal to r minus r1 squared. So in other words, that thing in there is equal to f of r. So I can just say that thing in there is equal to f of r. That thing in there is equal to f of r, okay? And 2 lots of r minus r1, so in other words, 2 lots of r minus r1 is equal to f of r. So put those two things together, and I end up with f dash of r, f dash of r. So basically, if I rewrite this, I can rewrite it as x to the power of r times f dash of r, plus f of r times natural logarithm of x times x to the power of r. Okay. Well, look. Okay. And if I put r equal to r1 in, then I basically end up with this thing is equal to 0. Well, if I just rewrite these two things around the other way, so in other words, I write f dash of r times x to the power of r, f dash of r times x to the power of r, okay, are you happy that that thing there is my y1, okay, and that thing in there is my y2? Or I'm trying to show you that that thing in there is my y2. Of course, I've shown you what the answer is for y2. But that thing in there actually ends up coming as my y2. Now, this takes quite a lot of work to show mathematically. But the idea is that because this is just equal to some constants, so c1, let's say, this is equal to c2, it looks something a bit like that. Then therefore, it follows that y of x is going to look something like this. So basically, what I'm trying to show you is that y2 is equal to that. Now, like I say, it takes a lot of work mathematically to show it. But basically, the idea is that because at r, r1, this thing goes to 0 and this thing goes to 0. I end up with the right hand side is equal to 0. Okay, so therefore, the idea is then that we just want to try and pull a solution out of the wreckage. It's all burnt down. We've just shown that this right hand side here is all equal to 0. We've shown that this right hand side is all equal to 0. But we can pull a solution out of the wreckage, and the solution is that because this is x1, this x to the power of r is y1, okay, then this thing here must be y2. This thing here must be y2, okay. Again, it's a lot of work mathematically. It's kind of I can show you why it's true. I'll give you an idea of why it's true, but I can't necessarily show you explicitly how it's true. It takes a lot of mathematics to show you why it's true explicitly. But yeah, this is basically the idea. So basically, this is the two solutions we end up with. We end up with y1 is equal to x, so x to the power of r1, and y2 is equal to ln x times x to the power of r1 as well. So yeah, it's kind of, if you go back right to the very start of the video, this is like the thing which differentiates or distinguishes y1 from y2. Okay, and again, you can verify whether they're linearly independent or not just by taking the Vronskin of these two solutions. So the Vronskin is equal to y1 and y2, differentiate it, so y1 dash and y2 dash, and the Vronskin basically ends up as, I'll leave you to verify that yourself. Again, you're going to have to use the product rule there, but basically the Vronskin ends up coming out as x to the power of r1 times ln x to the power of r1. You can see that just by simply replacing the two things in there. Okay. Then when you differentiate it, you end up with r1 times x to the power of r1 minus 1. Okay. And in here you end up with x to the power of r1 ln x. R1 ln x. This is where it gets a little bit messy. R1 ln x times x to the power of r1 minus 1 plus x to the power of r1 minus 1. It just comes out as a chain rule. You verify that, okay, and you basically end up that do a little bit of simplification in there, nice little bit of cancellations and stuff such like, and you basically end up with x to the power of 2r1 minus 1. I'll leave you to verify this, okay, which of course can't be 0. Can't be 0 for as long as x is not equal to 0. So as long as x is not equal to 0, we end up with a linearly independent solution. So again, I'm just showing off at the end there. I'm just showing that I know how to show whether they're linearly independent or not, and get used to the idea of showing them that they're linearly independent, such like. Okay.